I want to talk about a special type of relation now called a function. And we've probably seen functions in some respect in our mathematical careers so far in high school or something like that. But we're going to talk about what a function is in terms of a relation here. And one metaphor you can use, functions are kind of input-output machines. So it takes an input and it delivers a unique output. This word "an" is important here. I actually mean exactly one. That's the idea of a function. Well, what that means basically is we can input everything in our domain here into the function, and we get exactly one element in our codomain. We usually write functions as the input a to b like this with an arrow between them, and we label it with some name. F is a common name for a function. So a function from a to b, we write like this. And again, more formally, what's the property of a relation that makes it a function? It's that for every element in the domain A, there's a unique element in the codomain B, such that A is related to B under this relation. We call it F. Every element of A is related to exactly one element of B. And thinking of it as an input-output machine, we usually write, instead of writing A, B like this as an ordered pair, we usually write F of A equals B, or whatever name of your function is. So let's determine if the following relations down here are indeed functions. So let's use kind of that digraph idea. So we have in our domain, we have 1, 2, and 3. And in our codomain, we have A, B, and C. So it tells us that 1 is related to A. It tells us 2 is related to B. And it tells us that 3 is related to C. You can see, it's a little check of every element in your domain, how many elements in the codomain is it related to. 1 is related to exactly one thing, A. 2 is related to exactly one thing, B. 3 is related to exactly one thing, C. So this one is indeed a function. Let's look at F2. I'll do F2 in a different color. Maybe I'll do it in green. Maybe I'll just write down first this guy was F1. Now let's do F2 in green. So we have 1, 2, 3, A, B, C, same as before. We have 1 is related to A, 2 is related to B, but now 3 is related to A. And this is F2. And we check. How many elements is 1 related to? 1 is related to exactly one element, A. 2 is related to exactly one thing, B. And 3 is also related to exactly one thing, A again. So this is also a function. The fact that in the codomain nothing is related to C, we don't care, really. Being a function is, in some sense, is a property of what's happening in the domain. That every element of the domain is related to exactly one thing in the codomain. To know it's a function, we don't care which element in the codomain it's related to. So both of these relations are indeed functions. Maybe let's see one that isn't. So maybe you had something like this. Maybe you want 1A, 1B, and 3C. Let's say you had that. What would that look like? F3, again, 1, 2, 3, A, B, C. 1's related to A, 1's related to B, and 3 is related to C. And remember, in order to determine if something is a function, you have to check every element of the domain. Is that related to exactly one thing in the codomain? Well, here, 1 is related to 2 things in the codomain. It's related to A, and it's related to B. So this is no good. The number of things that 1 is related to is 2. So right there, we can stop. We can just say, not a function. No good. But just for elucidation purposes, let's keep going. 3 in some sense is okay. 3 is related to exactly one thing. 2 here, 2 is related to 0 things. So this fails as well. So this is related to 0 elements of B. So it's not related to exactly 1. 0 is not 1. So there are in fact 2 counterexamples to this being a function, 1 and 2. Let's scroll down and do a few more. Okay, I think it's a good idea for you guys to try this. So let me indicate first that our all relations here are from A to B. So G1 and G2 are indeed subsets of A cross B, just so we know which way the relation goes. Okay, pause the video now. Try it yourself. Okay, now that you're back, again, we can see this using a digraph. So the set A, our input set, our domain, is all natural numbers that are less than 6. They are, of course, 1, 2, 3, 4, and 5. There's our A. And our B is all natural numbers. So I'm not going to list them all, of course. There's infinitely many. Let me list a few, and I'll put some dots. It doesn't matter. Okay. So G1, let's do in blue. So here we have 1 is related to 1, 2 is related to 2, 3 is related to 3, 4 is related to 4, 5 is related to 5. Every element of A is indeed related to exactly one thing in B. This is indeed a function. The second one, well, just looking at this, I think you can tell this isn't a function because, say, 2 is not related to anything. Neither is 5. So the number of elements that 2 in the domain is related to is 0. It's not 1. Same with 5. 5 is related to 0 things. We need 5 to be related to exactly one thing, and 2 to be related to exactly one thing in order for G2 to be a function. G2 is not a function in this instance. All right, let's look at these 3 examples here. So H1, H2, and H3 are all relations. I'm telling you the relation. You got to be careful. There's a few symbols here. Square root and a fraction with an x in it. These aren't defined for all values of x. So if I put in, say, a negative into a square root, I can't take the square root of a negative number, so that's just not defined. So, looking at the first one, well, is this a function? We have here that the domain and the codomain are the real numbers. So, I can rewrite this using our function notation by saying f at x is square root x. Is this a function on the real numbers? And that's important that I do specify the domain and codomain here. So the domain is the real numbers. So pause the video and think about that. Okay, now that we're back, well, what if I put in -1 into my function? I look at f of -1. Well, that's the square root of -1, and this doesn't exist. That's nothing. So that means -1 is related to nothing in the codomain. So we can write -1 is not related. So what do we call this? H, not FH. H, let's call it A, is not related with that relation H1 for any A in the reals. So that means that this is not a function. Let's look at H2. Well, H2, you could think, well, you just take 1 over any number you like. But remember, 0 here can't go in the denominator. So here the function would be, maybe I'll change color to make it a little more easy to see. So let's look at 0 and 1 over 0. Well, f of 0 is 1 over 0. That doesn't exist. That's not a real number. So this guy here, that's nothing. So that tells me that 0 is not related via H2 to any value A for any real number A. So this is not a function either. What about the third one? What about H3? Well, this one, let me make it clear, this is a square. Well, now our function is f at x equals x squared. That's the function notation for that ordered pair. And I think it's pretty clear that for any value a, you've just squared, you get a squared for any real number a, and a squared is, of course, a real number. If you multiply a real number by itself, you get a real number. So this indeed is a function. In fact, every number is related to exactly one number, its square, via this relation. I called it, what am I doing? And actually, I'm being a little sloppy here. Let me be less sloppy. So I wrote f here, but my relations are h1, h2, and h3. So really, I should be writing h1 of x is square root x. So I should be replacing these guys with h1s. Here, I should say, instead of f at x, I should be saying h2. And here, because I called it h3, this is h3 at x, not f. Just because that's the name of the function. Okay, so we talked about 3 potential functions and which was actually a function. So let's move on here. And quickly, to talk about equality of functions, it's exactly what you'd expect. If we have 2 functions with the same domain and codomain, we'll call them f and g. They're equal if the outputs equal at every input in your domain. So if I plug in a into f and a into g, I get the same output. F at a equals f at g. Now here's a good little example. So a good thing to ask is, well, if you have 2 finite sets, how many different functions exist between them? So let me get you started off here. Let's say A had m elements, I guess, and the labels of the elements don't matter, so I'm just going to call them 1, 2, 3, all the way to M. And B, well, B can have a different number of elements. B can have anywhere from 1 to, let's call it, N elements. So we're saying that the cardinality of A is M, and the cardinality of B is N. And just to make things a little bit simpler so we don't have to deal with special cases, let's say both of these sets here aren't the empty set. So A and B aren't the empty set, not equal to the empty set. Okay. So let's think about how many different functions we can make. Remember, it's a function from A to B, so each element of A has to be related to exactly one element of B. And if you say where 1 goes, it doesn't affect where the next element can go. 2. 2 could also go to 1 if 1 goes to 1. So think about that. My first question is, how many different choices are there for the output of 1? Think about that. And then think about, all right, how many choices are there for the output of 2? So think about that. And hopefully you can kind of reason what's going on with the choices for the outputs of all of these M numbers in A. And see if you can put that together to come up with how many different functions there are from A to B. So pause the video now and try and think about that. Okay, now that we're back, well, 1, let's start with the element 1 in the domain. 1 can go to any one of these N elements. 1, if you wanted to, it could be mapped to 1, it could be mapped to 2, it could be mapped to 3, 4, 5, could be mapped to N, whatever. So, the number of different choices for the output for when you plug in 1 into your function is N. There's N choices. So let's say number of functions. Well, there's N choices for the output for 1. Okay. Well, what about 2? How many choices are there for the output of 2? Well, it doesn't really matter what you choose as the output for 1. You can still choose that to be the output for 2 as well, or you could choose something different. There's still N choices for the output of 2. It can be any of the numbers from 1 to N. There's N different choices. It can be any of those. So this here is the output for 2, and we can keep going like that for every number. It doesn't matter if a number gets used in the codomain, it can still be the output for any element in the domain. So we always have N choices. So this is M times. So for each of these M numbers, we have N choices for where they map to. So this is going to be N multiplied by itself M times, which is N to the power of M. Or if you like, in terms of set notation, it's the cardinality of B to the cardinality of A. All right. Now I want to define what a composition of functions is. So that's what I want to talk about now, what a composition is. And let me talk about the idea of it first. So we're thinking of a function like a machine. So imagine here is our machine. And let's say this machine is F. And it takes an input, and it gives some sort of unique output. And let's say you can input things from a set A, and it outputs things from a set B, usually via some rule. And let's say, again, we have another function. Let's call it G. And again, it has an input and an output. If the input set lines up of G lines up with the output set of F, well, you can just glom these two functions together. So you can make the composition. We usually write it as like this, G circle F, meaning do F first and then G. And what this looks like in terms of a machine, you're just kind of putting these together. So we do F first, and then we just attach the second function to it, G. So we're joining these pipes here. So here's G. And remember, we put in something from the set A, then F turns it to something in the set B, something in that codomain, but that's also the domain of G, so you can glom those pipes together. G accepts inputs from set B, so you're good to go, and it outputs something from set C. So this machine here, we can just like put a big box around it and call it the composition. So that's what's going on. You're just kind of hiding it in a big box, and you're calling this G circle F. That's the name of our new machine. So that's how the composition of two functions works as the idea of it. Let's have a look at the specifics. Let's have a look at what's going on more precisely. Let me see if I can scroll up here. Okay, maybe there will do. Okay, so we have a function with a domain A and a codomain B. We call that F. Another function, G, from B to C. We call the composition of G and F written G circle F, and that's from A to C. And it's where G of F of A, we read it as G of F. We're plugging in F of A into G for all A in A. And of course, the codomain is C. So let's have a look at this. So we have a function F here. You plug in a natural number. It spits out a fraction. G, you plug in a fraction. It spits out a real number. And here's how the function is defined. Or I should say both functions are defined. F of n takes n as an input and outputs n over n plus 1 squared. And what it does for G is it takes the square root of the absolute value of whatever fraction you put in there. So that's what G does. Remember, the input here is a rational number, and the output, well, it can be any old real number that you like. So let's determine G of F of 1 and G of F of 4. And maybe as an extra problem, I'll just write this in. Determine a simplified formula for G of F of let's say n. Okay, so it might be a good idea to pause the video now and try this yourself, at least these two parts for sure. Remember, you're going to have to work out what f of 1 and f of 4 is first before you plug that in to g. Okay, let's go ahead and do this. Okay, so we are looking for, first of all, g of f of 1, which is g of f of 1. And g of f of 1, well, we know how to figure out what f of 1 is. We have a formula here. It's n over n plus 1 squared. So this is going to be g of 1 over 1 plus 1 squared. And we can simplify this. This is g of, well, 1 over 1 plus 1 squared is 1 over 2 squared, which is 1 over 4. So f of 1 is a quarter. And now we take g of it. G of a quarter is the square root of the absolute value of a quarter, which is, well, if we think about it, this here is going to be positive, so we can take the square root of the absolute value of each of the numerator and denominator separately. So this is going to be the square root of the absolute value of 1 over the square root of the absolute value of 4. Well, the absolute value of 1 is 1. 1 times 1 is 1, so the square root is 1. And with 4, the square root of 4 is 2. So we have g of f of 1 is a half. Let's continue on. Let's do g of f of 4, same idea. G of f of 4, well, that's going to be g of f of 4. So that's g of, well, f is n over n plus 1 squared. So this is g of 4 over 5 squared, which is 25. And now this is going to be, well, the square root of the absolute value of 4 over 25. And you can see, indeed, this simplifies similarly to the above to 2/5. So we have g of 4 is 2/5. And in some sense, you could think these absolute values are doing nothing. And you're right, they aren't in this composition. But in general, remember, you can plug any rational number you like into g. You could have some sort of negative number. So just to make sure that g is indeed well defined, that we have exactly one output for every input, these absolute values make that so that we're never taking square root of a negative. And if that was the case, then our function wouldn't be well defined. Okay, let's do the third bit. So we want to find a simplified formula for g of f of x. And that's going to be, well, g of f of x. And we know what f of x is. Or actually, I shouldn't use x. Let me erase this. X is a poor choice because it should be n. N is our natural number, so let's go with that. So we know what f is. F is n over n plus 1 squared. So we have g of this expression. And, well, what does g do? It takes that expression in there, and it takes the absolute value and then square roots it. So it's the absolute value of n over n plus 1 squared. And again, well, we can just take the square root of the top and the square root of the bottom separately. Everything's positive, so we're good to go. So this is the square root of the absolute value of n over the square root of the absolute value of n plus 1 squared. And the square root of the absolute value of n, remember, we can think of this. Remember, n is always positive because n comes from the natural numbers. So in this composition, this absolute value is doing nothing. So just in this composition, we can drop it. So we can simplify the top to just the square root of n. And the bottom, well, we're squaring something and then taking the square root. The absolute values in some sense are doing absolutely nothing here, because if you square something, it's going to be positive anyway, and the bottom's always positive. So this is just the square root of n plus 1 squared, which is n plus 1. And this is pretty much as simple as we can make this expression. So we have the composition, g of f of n is square root n over n plus 1. All right, let's do one more example. We have this f of x is 2x plus 1, and g of x is x squared minus 3. We have that the domain and codomain of both of these functions are the real numbers. So we can take the composition, g of f. The codomain of f lines up with the domain of g, so we're good to go. And in fact, we could compose these two functions the other way. Let's do f of g as well. So let's do both of them. Okay, so same idea as the previous question. Maybe a good idea is to pause the video and try this yourself. See if you can find both of these compositions. Okay, now that you're back. Well, we're looking for g of f. So g of f of x. Well, that's going to be g of f of x, which is g of, well, we know f is 2x plus 1. So, what is g saying here? G is saying take whatever your input is, square it, and then subtract 3. So if we input 2x plus 1, well, we're going to square it and then subtract 3. So this function notation is saying whatever the input is, this is the rule to get the output. So our input in this case is 2x plus 1, so we're squaring it and then subtracting 3. And now it's just a matter of simplifying. Expand this out, we get 4x squared plus 4x plus 1 minus 3. So we can write this as, well, 4x squared plus 4x minus 2. And if you like, let's factor it at 2. And we get 2 times 2x squared plus 2x minus 1. Okay, and you might think, does this factor? This does not factor into nice ax plus b integer type factors, so we can just leave this as 2x squared plus 2x minus 1. If you're unsure how to see that, remember, for factoring you need two numbers that multiply to give you 2 times -1, so -2, and add to give you this number, add to give you 2. And there are no two integers that do that, so we can't factor this in the integers anyway. So we did g of f. Let's do f of g of x. And again, remember, g is the first function here. So the output of g, the codomain of g, has to match up with the domain of the second function of f. Even though they're written f of g, it works like a backwards order, just because we can think of it more like this notation here. So we do g first, and then we do f. So the codomain of g lines up with the domain of f. So this is indeed, oh, it's the wrong pen, f of g of x. And we know g of x is x squared minus 3. So what's the rule f say? It says take whatever your input is, multiply it by 2, and add 1. So that's what we're going to do. We're going to take our input, x squared minus 3, multiply it by 2, and add 1. We simplify this to x squared minus 6 plus 1, which is 2x squared minus 5. So there we go. We worked out both the composition g of f of x and f of g of x. Now, a couple of notes, and I want to do one example for each of these notes. So, first of all, we call a function well-defined if it's actually a function. So, if every input gives you exactly one output. So, if a equals b, then of course, if you plug it into the function, you're going to get the same value. So, if two inputs equal, then of course their outputs would equal, because inputs need to have a unique output in a function. And you'd think, well, this is kind of weird looking. When would this even come up? And the example is, sometimes you can express numbers in different ways. And if you express it in a different way and it gives you a different answer, then it's not a well-defined function. Let's do an example first, and then we'll talk about implied domains, which is the next note. So this is kind of the prototypical example for a function that isn't well-defined. So this function goes from the rational numbers to the integers. And the way we define it is we plug in a rational number, and the output is just the sum of the numerator and denominator. Okay, so we want to show that this is not well defined, that if we plug in an input that's the same number, just written in a different form, then we get a different output. So that's what's going on here. This isn't a well-defined function. So here's our note, and here's a really simple one. Well, obviously, a half is the same number as 2 quarters, just expressed differently. Okay, so note that j of a half is 1 plus 2, which is 3. But j of 2 quarters, remember a half equals 2 quarters, just written differently, is 2 plus 4, which is 6. But these two outputs, 3 and 6, aren't the same, even though I plugged in the same number, just written in a different form. So the inputs equal, but the outputs don't. So that means our function j is not a well-defined function. It's some relation for sure, but the relation doesn't satisfy that unique output property of a function. Okay, and the next note I want to talk about is the idea of an implied domain. And a lot of times, especially if you've taken something like pre-calculus or even calculus, you'll deal with lots of, we call these rational functions, so polynomials in a numerator and denominator. And we'll express f as a real function, but it's implied that you're not allowed to input anything where the function is not defined for. And in this case, it will be when the denominator is 0. So, that's what we're going to do in our next example. We're going to find the implied domains of these two functions. So the first one is this rational function. And the second one is 1 minus e to the sine x. Okay. So, let's go ahead. So this is x plus 1 over 2x squared minus 2. And note, f of x is not defined if the denominator here, 2x squared minus 2, equals 0. So that's what we're going to do. We're going to find all places where 2x squared minus 2 equals 0, and we're going to say we're going to exclude those from our domain. Okay. So, 2x squared minus 2 equals 0. Well, let's factor in a 2 here. So we get 2 times x squared minus 1 equals 0. And hey, look at this. We have a difference of 2 squares. So we can factor that as x minus 1 times x plus 1. And that equals 0. So this means that this equals 0 when x is positive or negative 1. So, the denominator will be 0 when x is 1 or negative 1. So we want to exclude those from our domains. So the domain of f is the real numbers, but we don't want the elements negative 1 and 1. So we'll just use that set difference notation here. And well, what about 1 minus e to the sine of x? Well, for g of x, which is 1 minus e to the sine of x, well, what values is sine allowed to take? Well, you can plug in any x value for sine and you'll get some output. There's no excluded values for sine. For e, again, there's no excluded values for e either. So in fact, the implied domain of this is just all real numbers. You can always plug in any value of x and get something defined here. Because remember, for sine, the graph of sine looks something like this. And it just keeps repeating ad infinitum. There's not a place where it's not defined. That's a rough sketch of sine of x. And e to the x, same idea. That looks roughly like that if you graphed it. So you can plug in any number into e to the x and you'll get some output. There's no place where either of these functions is not defined. So this guy is for sure going to be defined for all x. So its domain is just all the real numbers. And just a few little reminders here. This will be important when we're talking about implied domains of other functions. So, I'm sure most of you know this, but the domain for the function square root x, well, you can only take square roots of non-negative numbers. So the domain of a square root is indeed, well, all real numbers x such that x is greater than or equal to 0. So that's the domain of a square root. And another one that comes up a lot is the domain of the log of x for any base. Let's call it log base a of x. Well, logs can only be defined for positive values. So the domain for a log is indeed all real numbers such that x is positive. It's greater than 0. And just to have this down as a little reminder as well, if you have some sort of rational function, so f of x over g of x, if you have some sort of fraction like that, the domain here is all real numbers such that, well, you want f of x to be defined and g of x is defined and it doesn't equal 0. Because remember, you can't have a denominator of 0, else the expression is undefined.